Okay, welcome everybody to Optimization Oslo. We're very happy to have Ronny Bergmann from the NTNU, who's going to speak today about non-smooth, non-convex optimization on Riemannian and manifolds.
Thank you very much, Thomas, for the invitation and for the possibility to give a talk here. Yes, I want to talk about non-smooth and or non-convex optimization on Riemannian manifolds. And since there's quite a few people involved, I decided to first start with basically an overview of people that were involved. I will first start to talk about the non-smooth case, and that's the first row. Roland Herzog, Mauricio Silva-Lozero, Daniel Tambrink, and José Vidal-Nunes. For the non-convex case, it's people from Brazil, namely Orizon Pereira Ferreira, Giancarlo de Oliveira Sousa, and Eliana Meneses Santos, who wrote his PhD thesis in that area. And the last part will be a little bit about software, and that's joint work with Zeth Exon and Mateusz Baran in Julia then. Okay, let's get started. What's the motivation here? We might have a problem like the Rayleigh quotient, which is not the practical way how you would compute the smallest eigenvector of A, but it's a good illustration of what might happen. So if we have an eigenvector x star to the smallest eigenvalue lambda of A, then every scaled version of that gives us the same cost function in x transpose ax divided by the norm, because we divide by the norm. Namely the lambda that is the smallest eigenvalue. But that means that we don't have isolated minimizers. In other words, if you would write down Newton's method, it would just run along this line to an infinitely long vector. So it even diverges on this problem because we don't have isolated minima. So one solution for that would be to constrain ourselves to say we only consider unit vectors. But then we would end up with a constraint problem. So something like augmented Lagrangian or exact penalty method, all these would be classical ways to tackle that. But today, we want to utilize more like the geometry behind that. So we want to use the geometry of the sphere. We can leave out the constraint because we restrict ourselves to the sphere anyways. So we end up with an unconstrained optimization problem with the disadvantage that if we have 2 points on the sphere and we add them, we leave the sphere. So we have to take into account that we have a certain geometry that's non-Euclidean, but we end up with an unconstrained optimization problem that would allow for Newton's method again, because we're unconstrained in the manifold like the sphere. So we have an unconstrained optimization problem on the Riemannian manifold with the maybe drawback or the interesting part, depending on your viewpoint, that we have to consider analogous methods on Riemannian manifolds then. So that's the motivation here. We can turn that a little bit further if we're interested in a basis for the first k eigenvalues, so the space that the eigenvectors of that one span. Let's assume they are all ordered and the first k1 are unique. So from k to k plus first, there's an actual step in the eigenvalues. Then we could write down this problem as find the basis x transpose x equal to I. So we still want to stick to unit vectors that are orthogonal even. So we have an orthonormal basis of a space. And then we minimize the same idea. This would be an optimization on the Stiefel manifold. So this STNK is the Stiefel manifold. But the problem here is, though that is already a Riemannian manifold problem, that if I rotate my basis without changing the subspace I'm considering, that again doesn't change my cost function, because I'm still considering the same subspace in our end then. So we are maybe not interested in the basis itself, but just in the subspace. So we could also say, let's find the best subspace. So we consider the so-called Grassmann manifold, which is the Stiefel manifold, but modular rotations, which again is an optimization problem on a Riemannian manifold. now the Grassmann manifold. But the one difference is we're not speaking about something that's inherently just vectors like the basis before, but now we speak about spaces. They are still represented in numbers by the x that is the basis, but we basically identified every basis that spans the same subspace here. So we end up with a manifold that's maybe not so easy to tackle or to see as the Stiefel manifold, where we still have every element is one X matrix somewhere in the space of matrices. Okay, so much for the motivation here. In general, we want to find numerical algorithms that minimize a function f that maps from the manifold into the extended real line. And with numerical algorithms, I mean, the easiest ones would be gradient descent or something like quasi-Newton. But for us, even further, our f might be non-smooth and or non-convex. We will start with non-smooth and then consider non-convex. And the manifold M might even be something quite high dimensional, a few thousand dimensions. So imagine, for example, the 1000 dimensional sphere in Rn, where n is then 1001. Or that we have a certain Stiefel manifold of a quite high dimension for the examples that we just had. Okay, let's take a step back and discuss a little bit what we mean by Riemannian manifolds informally, and that's from the book by Abzil, Mahoney, and Sepulchre from 2008. It's a set M with a suitable collection of charts that locally identify every small set of the manifold with some RD, where D always has to be the same dimension. And at every point, we can measure basically angles between directions that point away from this point, or in other words, a smoothly varying inner product on the tangent spaces. Again, the easiest thing to imagine is the sphere, S2 and R3. Then every tangent space is really just the tangent plane to the manifold. And if I move the point where the tangent space is at slowly along the manifold, the inner product should also change in the same smooth way. But it might depend on the point P if you want to, where we're at. But it should be continuously varying. That's maybe the informal definition that we want to work with. And to fix the notation a bit, the first thing we want to consider is the exponential map. That is, we are at a point P, and I've drawn one here. And just for reasons of illustrations, this dashed line is not really a line. This is meant to be the tangent space up here. And so it's actually attached to the point P, but it's moved away a bit for illustration reasons. Then I have a direction X that I want to walk into. And the exponential map would realize this walking into a direction by taking a geodesic, which is an acceleration-free curve. And locally, that's unique. And walking into the direction means following this curve to some point Q. The logarithmic map is the inverse question. So I'm having 2 points, and my question is, what's the direction I have to walk into to get there? Which already gets us to the first problem. If the points P and Q are north and south pole on the sphere, there's no unique answer for log. Though, if we take as a manifold the Euclidean space, log is just minus, the exponential map is just plus. Informally, you could have that in mind as the logarithmic map might not be globally defined. So minus is maybe not always available if you want to draw that comparison. Then the tangent space is denoted by TPM. At every point P, the inner product might depend on the point P, so we use round brackets and the P as an index. And the last thing we need is a way to identify different tangent vectors from different points, and that's called the parallel transport. And in Rn, that would really just be the parallel shift of my vector from the point P to Q. Here it might change slightly, but I try to illustrate that with this slowly dotted lines that go along there. Okay, so much for the notation. The next thing we have to discuss is convexity. So the first thing is a set is called strongly geodesically convex, and the following I will just say convex. If for all P and Q, the geodesic that connects both is unique and lies again in C. So we are not allowed to take north and south pole, for example, in sphere, because then the geodesic would not be unique, and I cannot speak of the geodesic. So here I enforce that they are unique and lie completely in the set C. Then I call C a convex set on the manifold. And with convex sets, I can define convex functions. So a function is called convex if it's convex along geodesics. So this is the composition of F and the geodesic. And if that's convex in the classical case with T as a parameter, then F is called geodesically convex. And I will again in the following just say convex to keep my wording a little bit simpler. Okay, so much for the convexity. The last thing, second to last thing we need is the subdifferential, which nearly works like the classical subdifferential. So again, this inequality here, f of q is larger or equal than f of p plus this nearly linear term. It's a linear term in the tangent space, or in other words, the psi is actually from the dual space, so it's a linear function on the tangent space. And we have to localize this to some set C, and can usually not take the whole manifold because we have a log in there, and that's not globally defined. But that's the subdifferential if we have our set C from before, the subdifferential of F. And if F is smooth enough, then it's just containing the gradient again, as usual. Okay, the last thing is just a notation. So if we have the inner product and the duality pairing with the tangent space and the dual space, then mapping between the linear functional psi and a tangent vector x is done by, well, the one way by flat and the other one by sharp. So that's the musical isomorphisms as, for example, defined in Lie. But that's just identifying the linear function on the tangent space with a tangent vector to go back and forth between those. Okay. The last thing we actually need to get our algorithm starting is the proximal map, where we say, instead of minimizing f, let's minimize f with the restriction that we don't want to run too far away from our input point q. So we minimize f with a certain weight lambda up front, but we also want to stay close to the input point p. This is the geodesic distance, so basically the length of the geodesic that connects P and Q. So this distance squared, in the Euclidean case, this is just the difference in the norm. And then you get the classical proximal map. But here, again, with the distance on the manifold, and then the lambda f, as usual with the lambda for the proximal map. For the Euclidean case, that goes back to Moreau and Rockefeller, and on manifolds that was, for example, introduced in Oliveira Ferreira about 20 years ago. The properties here, if we have a minimizer of f, then that's a fixed point of the prox. So prox lambda f of p star is p star. If f is proper convex LSC, so lower semi-continuous, then this minimizer is unique. The caveat here is minimizing or computing the prox in general is as hard as minimizing f itself. So in practice, numerically, that might not be the thing you want to do. But if there's an easy way to compute the prox, then the proximal point algorithm, so iterating the application of the prox, converges actually to p star. So that's a nice thing to know of the proximal map, that the PPA converges. We will meet that later on. Okay, let's get to the first topic, which is non-smooth splittings and the question of duality. If we look for algorithms that minimize the sum f of p plus g of p, we could use the so-called cyclic proximal point algorithm, given that the prox of f and the prox of g are easy to compute. That doesn't say that the overall minimization is easy, just that the single ones are easy. Then we could iterate through those two proxies back and forth, basically, because it's just two. Or you could use the so-called Douglas-Rushford algorithm. For two, it's Douglas-Rushford. If it's more than two, it's called parallel Douglas-Rushford. Those two exist on manifolds, 2014 and 16, basically. But if we now take a step back and say, the manifold is too complicated in Euclidean case, There's a few works by, for example, Simon Setzer, that say the Douglas-Ashford algorithm that we already have on manifolds is equivalent to the primal dual hybrid gradient algorithm or the Chambord-Pock algorithm, which is named for this paper Chambord-Pock, but it also was part of the works of Kremers and Bischoff as well. So, but the paper to usually cite is Chambord-Pock. The problem with that on manifolds is that involves duality, Fenchel duality, to be precise, and the dual space of Rn. So all linear functions on Rn. Now, the manifold M is inherently nonlinear by itself, so there is no linear functions on a manifold. So we don't have a dual space. But maybe we can still formulate something like a Fenchel conjugate to, that's the goal for the first part, come up with the Chambord-Pock algorithm. But for that, let's first look at the Fenchel conjugate. So the Fenchel conjugate is basically an extremum seeking problem. So I have this linear function psi x or psi transpose x in Rn, and I want to find the largest distance to f of x. That's the point x I'm looking for. And I know the point, but I'm interested in this distance actually. So I want to minimize the distance between the linear function and f. And I could rewrite that as an extremum seeking problem on the epigraph. That will also be my image on the next slide in this form. So instead of having this as its extra form, I could also say x transpose psi transpose x in the first component and -1 times f in the second. That exactly gives me the same, and I'm on the epigraph basically. And if I've done that once, I can do that twice. That's called the Fenchel biconjugate. So if I plug in f star, I'm looking for the largest psi, so that this one is maximal. That's called the biconjugate, or doing the conjugate twice. What does that mean in images? If we have this function here on the left, this one, and I'm specifying a certain psi, we are one-dimensional, so it's just a number, let's say something like -4, then the dashed line here has a slope of -4, and the maximum distance between my plot f and the dashed line is this distance here. And the alternative interpretation is I look for all tangent lines to my function f by shifting it down. And then I can see that I see minus the largest distance at 0. And that gives me the possibility to always basically look at one point. By moving it down to be tangent of slope -4, I can always look at 0 and look for the largest point there. And I can do that for other points, and I'm always measuring that now at 0 for reasons that will become clear on the next slide. And then that would be different sampling values of my Fenchel conjugate. And one thing you can already see is we basically approximate f from below by linear functions that are always tangent, but otherwise below. And if I would evaluate all of them, I basically get a plot of the Fenchel conjugate f star on the right-hand side. And on the left-hand side, you still see I could measure all these values, all the orange dots on the right, at 0. So that's one interpretation of the Fenchel conjugate. Now, the properties are f star is always convex, even if f is not. Then we have that the biconjugate is the largest convex function that's still below f. So f is not convex. It's the convex function that is basically the closest from below to f. If I have a certain relation in my x, let's call that the primal variable, that reverses in the slope, the psi, the dual variable. We have Fenchel-Moreau. If f is convex proper LSC, then the biconjugate is f itself again. We have Fenchel-Young. That's not so interesting. It's more interesting to look at subdifferentials. So psi is in the subdifferential of f. Then we even have equality. F of x plus the Fenchel conjugate xi is the inner product. Both of these just come out of the definition of the Fenchel conjugate. But I even have this nice duality between psi being the subdifferential at f of x is the same as x being the subdifferential of f star xi. So that's nice properties. And one goal for the Riemannian cases now to get most of these properties done as well. Not all of them will work because these might all work, but there's a few that don't work because there's too much linearity involved, and I would add p plus x or something, and that doesn't work on manifolds necessarily. Okay, so the idea now on manifolds is, first of all, localize ourselves to some set C that's convex around a point M, which acts as the zero where we measure again the minus the Fanti conjugate. That's why I introduced that in the graphics, that we don't have to run around too much. We measure at M. That's the idea. And then this is a bit technical. This one looks the same as before. I take now an element from my tangent space here, but this one is basically from the cotangent space. Xim. This is the same linear functional now just on the tangent space at M, and I'm subtracting f, and this going somewhere from 0, that was just f of x in the other case. Here I'm going from M into this direction x and measure there. So that's exactly the correspondence, just that this exponential map you don't see in the Euclidean case because there M is 0 and it would be 0 plus x. So that's a little bit of a trick. And this LCM is a little bit of a technicality that we need so that the exponential map actually realizes the distance and we don't have acceleration-free curves that are longer than the distance. Those exist actually, and that's a bit technical. So that's why we have to even localize this supremum a bit more than just a set C. And we can do that twice, even by choosing different points M and M prime and define the biconjugate, but in the following we will usually use M to be equal to M prime, just to basically measure at the same point. That's the idea. Let's check the properties again. F star M is convex on the cotangent space. If we have a relation on the set C in the primal variable P, that reverses for the dual variable in the cotangent space. Here we have one small difference. Not f itself has to be geodesically convex, but this function has to be convex on the tangent space, which is a vector space. Then we have the equality that the biconjugate measured at the same point is equal to f. And we can again do similar things with the Fanti-Young inequality. So this subdifferential can be classified by this equality. And we even get subdifferential equality, by this is in the subdifferential at f of p, but now here we have to be careful. First of all, this is the log and not the point p itself, because point on the manifold cannot be in a subdifferential. And here we have a parallel transport, because this psi p has to be moved to m before we can plug it in here. So it gets a little bit more complicated, but simplifies to the Euclidean case if you plug in m to be Rn. So it is a generalization in that sense. Okay. From that, we want to look at this problem now. The k could be the identity, then we are exactly in the case from before, but here k is a linear operator. Then we can apply the Fanti conjugate twice. Then we end up with this dual problem in the Euclidean case. Or if we check the optimality conditions, first order, these characterizations for a point to be optimal, critical. Or if you reorganize that a bit, this is the Chambord-Pock algorithm, which involves a sigma f prox in x and tau g prox, basically with respect to variable psi, because it's g star, and the so-called relaxation step. Here it's the dual relaxation because it involves psi. So that's Chambord-Pock. And we now want to mimic the same on a manifold. But the problem with that is, if we consider the same thing on a manifold, the k that I now called lambda, to really not confuse them, is inherently nonlinear. That's the first problem. And the second is that we will take the conjugate of g. I choose some n on the manifold n where g is defined. And then this one has to be convex. So g convolved together with the exponential map at n, that has to be convex. Okay, the saddle point formulation looks like this. And the last problem that it faces really this this lambda is inherently nonlinear, so we don't have an adjoint map lambda star, right, like we had the K star on the last slide. And the idea is from actually Tuomo, who did that on Rn for nonlinear case. We linearize the lambda or first order Taylor the lambda and get to this formulation. And that boils down to this one being a linear operator on the tangent space. D lambda is the differential, and that's a linear operator. And then we have D star lambda as well. Okay, with these ideas, this is the Riemannian Chambeau-Pock algorithm. It's the exact version because here we use lambda and not D lambda. And here you see D lambda star, that's the replacement for K star, and also boils down to that again in the Euclidean case, because K could be seen as linear functional, and the derivative, so the dk is then just K again. And here we have the primal update, that's the other formulation you can use. And if you have in mind that log is a minus and x is a plus, that again boils down to the Euclidean case. So in that sense, it's really, again, the complete generalization of that. Okay, so much for duality and the Riemannian Chambeau-Pock algorithm. For the second part, I want to leave convexity. Namely, we want to consider at least some structure still, difference of convex. So we want to minimize the function f. But the function f now has the specific structure that it's g minus h, where both g and h are convex, lower semi-continuous, and proper. Maybe only locally on some set C again. Global convexity is a little problematic. But this is the structure we have. But since h is convex and we have minus h here, that's concave. And we have something that's not convex overall, but a difference of two convex functions. That's what we want to minimize as a second task for today. And the ideas are now as following. Let's again first consider the Euclidean case. At every point xk that we're at, we could say, well, h is maybe not so nice when we consider minus h to be concave, but we could look at the linearization of h. So this is just the linear or first order Taylor of my function h at xk. And then I could minimize g minus hk, which is majorizing my original function from above. So I minimize that one instead. That might not be as good as the original, but it hopefully gives me a step forward if I take here a subgradient. The second idea, we could use duality theory, take the dual of h and the dual of g, and find a yk in this set that would be the same yk as above. Again, for the Euclidean case, you can easily write that down. For the Riemannian case, and that's exactly how the Brazilian group approached me, there was no fancier duality, so that cannot be done on manifolds directly. And the third idea was we can reformulate this one using a proximal map and end up with the so-called difference of convex proximal point algorithm. Good that we had the proximal point algorithm before. And in this formulation, in exactly this algorithm, that could be generalized to manifolds in 2015 by Sousa and Oliveira. And it was this is a speed up version a few years ago that accelerates that. So the idea 3 to reformulate the second one to have a DC PPA, that's already a few years old. But the question was then, since all these three are equivalent in the Euclidean case, can we do the first two on manifolds? So can we do the linearization in some sense here, or can we use duality theory to find something in the second idea? Okay, for that, we actually needed another form of duality, which basically gets us rid of this point M where we measure, because we now take the supremum not only over all, so here it's again the supremum over M, and we can now globalize that because we're on Hadamard manifolds. Those are these of non-positive sectional curvature, where we don't have this limit with the convex set C. We can take C to be the whole manifold. And then now we define this one to be defined on all cotangent spaces, or the cotangent bundle, T star n. And basically the P that we have here is what before was our base point, but now it's a variable of the fancy conjugate. So here the domain of my conjugate is twice as large in dimension as my original function f. That's maybe a little bit surprising, but this fancy conjugate has a few nice properties like a separation theorem that we could prove. And here it's also more useful than the other one. Okay, with that, the difference of convex problem on manifolds is exactly this G minus H again. And we can use the Fantian duals from the last slide to state the dual, which, as in the Euclidean case, switches their order. So we apply the Fantian dual here and there, and then in the end, the order switches. But we get a minimization problem over the complete tangent bundle, which is twice the size in dimension. So it's maybe not so practical to boost up our problems to have twice the dimension and solve that instead. But at least theoretically, you can write that down and it's the same problem as above. So that's at least from theoretical viewpoint something quite nice, that the Fantian duality also explains the phenomena that we see in the Euclidean case already for the dual. And you even see that the infimum that we get here in the dual case is the same as the infimum in the primal case. That's actually a proof that Elisanderson Santos did in his PhD. Okay, so if we now consider these two problems, they are equivalent in the following sense. If I have a solution of my primal problem here on the left, P star, and I have a psi star, then this is a solution of the dual problem if psi star is in the intersection of the two subdifferentials at P star of H and G. That's one direction. The other direction is if this is a solution of the dual problem for some psi in this intersection, then P star is a solution of the primal problem. This again generalizes the thing that we know for the Euclidean case here to Hadamard manifolds. So much for that duality. Can we now actually do the algorithm that I said in idea 1 on manifolds? So if we would now again try to linearize our function, or first order Taylor our function, we would take xi from the subdifferential, so a cotangent vector, and do this duality pairing. Now the minus gets a log, and we have the duality pairing at pk, but this would be basically the linearization in some sense of h. And for the Euclidean case again, this would be exactly the linear function, and it would be easy to minimize. Here we then identify the xi star with an x and use an inner product. That's maybe easier to write or easier to implement. And locally, this one is less than h, so it's below because we have subgradient here. But that means that if we minimize again minus hk instead of h, we are above, and we iterate that. Sounds nice. So on hk, this function on Rn, this function hk is linear, super nice to minimize. On a manifold, this is not even necessarily convex, not even on a Hadamard manifold. So we end up with a subproblem that's maybe not so easy to solve. We will see that in a second. But so here's it again. That's the problem we have to solve. And we iterate this, and that's the Riemannian DC algorithm. The advantage here is that, I mean, we could at least quite systematically write that down and maybe do a gradient descent still. If it's non-convex, we are not yet guaranteed to find a minimizer with that, but we also just need a good idea how to continue. So it's not necessarily that we have to solve that to super high accuracy at this point. But that's then the Riemannian DC algorithm, difference of convex, that you can state with that. So as I said, this subproblem cannot be solved in closed form, but maybe approximating that gives us a good candidate where to continue and finding a stationary point for the problem we are facing. Okay, let's look at the convergence. If we have now a sequence from the algorithm from last slide, pk, and these iterates of the subgradients, xk, then if we have a cluster point, that's in, then it's in definitely the domain of G. And there also exists a cluster point of the xk's that is in here. And that means every cluster point is a critical point of F. Doesn't necessarily mean that everything converges, just if we have a cluster point, then it's a critical point of F. And if furthermore, G is sigma strongly geodesically convex, same generalization as for sigma strongly convex, then we actually have that we get a cluster point even convergence to exactly one cluster point. So this distance goes to 0 and is summable. So that means this distance goes to 0. In other words, I end up with exactly one limit point of my pKs. So we actually get convergence if G is a little bit nicer than just convex. Okay, before we come to numerical examples, a small advertisement block for software where all this is implemented. So I work in Julia, and the first package we derived, not time-wise the first, but the first one to present is Manifolds base, which just tells you how to implement a manifold abstractly in general. So we have this type abstract manifold that says every subtype of this is how a manifold should look like, and it contains information about the manifold itself if I don't know any point. For example, it would allow me to generate a random point on the manifold. That information should be stored in there. Something like the sphere needs to know its size, that it's d-dimensional. That's the information stored in such an abstract manifold type. Then we provide functions or signatures of functions like the exponential map, the logarithmic map, or if the exponential map is too expensive to compute, we might approximate that by a retraction, where you can have different methods. That's why we have an additional parameter called method. But that would be just a first order approximation basically of the exponential map, because it's cheaper to compute and still good enough to do the job. That's the idea. I mean, for the Euclidean case, this is not necessary because the exponential map is plus, and that's usually cheap enough. But on manifolds, that might be a problem that the exponential map is expensive to compute, and then maybe approximations are good enough. And we can also say that we have different embeddings or different groups. So we could also assign a group operation to the manifold to get a Lie group. That's done with so-called decorators. And the last thing we also have these, in Julia, quite important things, exclamation mark, where the convention is that the exclamation mark says the input variables might be changed. And the one that we do change is the one that's new here. The Q is basically memory for the result. So since we know the exponential map computes the point on the manifold, here we provide the memory already, so we spare memory allocations for the result. And that's available for all these functions. And also the ones that we recommend to implement, because these would fall back, the non-exclamation mark ones, to these and allocate upfront. Okay, with that, we implemented, and that's actually where my work with Zeth and Mateusz started, Manifolds.jl. And our goal was to provide just a library of manifolds. So whenever you come up with a nice manifold that you like, hopefully we already have quite a few functions implemented. Or if you don't, get in touch with us and we can probably help you to implement them in the framework from the manifold space part. And we also provide something like a generic way to define the tangent space or Lie groups or something like that. And here's a small overview of a few functions. I mean, the space is limited, so I had to shorten that down, but the sphere is available, the Stiefel manifold that we saw, even generalized in the sense that we can use another inner product than just X transposed X. The symplectic Stiefel on symplectic matrices, the same for Grassmann and generalized Grassmann, or for example, the group of rotation matrices, symmetric positive definite matrices, or something like the oblique manifold, and recently also Kendall's shape space as one of the manifolds that's maybe a bit more complicated that represents shapes. And so on and so forth. So again, that's not a complete list, but at least a first overview. And if you're missing one, then maybe get in touch with us and we can hopefully help. Yeah, the one thing that I didn't mention is we also automatically can do power manifolds. So imagine a grid of n by m pixels, where every pixel is on my manifold m. We got you covered. And the same for product manifolds. So if you have something that lives on the sphere times some Euclidean space still, we also have product manifolds very generically implemented automatically for all these manifolds. Yes, so much for that. The next package is the one that I started Julia with because I wanted to do that. Manopt.jl, which provides optimization algorithms on Riemannian manifolds. And the idea that we just base that on manifolds base. So any manifold that follows the first slide, 2 slides ago, scheme of implementing function works with all solvers here. That's the idea. And Manopt.jl is usually split into a problem P that has, for example, the cost in there or the manifold it works on and so on and so forth. And a solver state that says which solver we use and what state it is in, for example, which stopping criterion to use and so on and so forth. And then in general, one would just implement how to initialize the solver, set the variable that stores the gradient to the first gradient and so on and so forth, and how to perform the I step. Again, using everything that the problem provides, the cost, the gradient, whatever, and store an interim's results in the state that might be needed in the next iteration. That's the idea of this split. So then we get an algorithm that's still a little bit technical. So the next point is then to have something like just call gradient descent on my manifold M with F and the gradient of F. And then the first algorithm already runs. You might need something like a retraction, of course, on the manifold M, and your function F is something that you have to implement and provide, but then this one directly gets you going. So this high-level interface is always available for the ones that we provide in the package. And we also provide keyword arguments, so semicolon debug equals to do debug output, record output, cache interims results of, for example, the evaluation of F or the gradient. So if that's expensive, that we can cache those. And also, if you're interested in statistics, something like how often is the cost function evaluated, that's also available. And a certain library of step size functions, AMIO line search, Wolfe conditions, and stopping criteria might also be interesting. Those can just be used for any of the solvers that have stopping criteria where it's useful. I mean, the max iter stopping criterion is again then the easiest one to use. And I'm not the only one to do that. There's the original package that started the Manopt name by Nicolas Baumal and co-authors at manopt.org. Then there were Sebastian Weichwald, Jamie Townsend, and Niklas Köpp doing PyManopt, the same idea in Python. And then there's Manopt.jl, the Julia variant. But they all follow the same idea, having an abstract manifold in mind, doing the algorithm independent of the manifold. And then the MATLAB and the Python version have the manifolds included. And in Julia, the idea is the manifolds are in a separate package because modular is the way to go in Julia. And to summarize the software part, this is an overview of the algorithms available. For the Nonsmooth case, Chambol Pock or Douglas Rushford are the interesting ones, and we will also see cyclic proximal point in a second. And for the non-convex one, difference of convex, or the DCPPA that we at least saw on one of the slides, are the ones that I want to mention, and the whole one, all of them can be seen at manopt.jl.org. So for our case, this is the generic call to difference of convex. We need M, we need F, we need G, and we need the subparameter of H, and we need a starting point. That's everything we need. So these are the functions we have to implement, F, G, and the subgradient of H. If you also provide H or the gradient of F, we can usually even provide better stopping criteria. But this is basically the minimal requirements to run the algorithm that we need. with this, the subproblem that I talked about is automatically generated and also solved with its cost and gradient, and then something like a gradient descent. But you can also, with substate equals as a keyword here, provide your own solver that should solve that and set specific parameters if you want to. But if you don't think about it, it at least tries to do something reasonable with the subproblem by itself automatically. And the whole documentation can be seen on the homepage for the solver again. Okay, let's get to numerical examples because we're also already nearly at the end of my talk. The first one is L2TV. So we have an image of D1 by D2 pixels of our manifold N. And then we want to find something that's not too far away from the original image Q. So that's the P we are looking for. That still has, this one says the logs should be small in norm to the neighbors. In other words, we want to have something where neighboring pixels are nearly the same. And if you have something noisy, then the denoised version would be something where that's flatter than the noisy rough image before. And that originally is the Rudin-Osher-Fatemi model, but this was generalized to manifolds, for example, by Lellman and colleagues, or by Weinmann and colleagues a few years ago. And this would be one example. So this would be something where we see a certain gradient in this is 3 by 3 positive definite matrices, asymmetric ones, visualized as ellipsoids with the eigenvalues. And here you can see a small gradient from just a circle, a sphere, to something that's more like cigar-like. And here it's all more like two different values left on that side. So that would be anisotropic TV, where alpha from the last side is 6. That's not the main point here. We are running an optimization algorithm to find this one. That's the story. And the first one we can run is just CPA. I would call that the working horse that does the job. But it takes a while, and we don't have a proper stopping criterion because it can converge arbitrarily slow. So this is basically just after 4,000 iterations or something like 20 minutes. I was a bit tired and was like, that's enough. So that's basically our benchmark, or the thing that was available before. And if we look at the cost, note that the iterations are already log scale. So it takes quite a while to converge. If we run instead of that the parallel Douglas-Rochefort on the same problem, 122 iterations and much faster. So this is the plot. And if we run jumbo POC, I would say we're maybe not beating parallel Douglas-Rochefort too much in iterations, but we are much faster in computations. So it's much cheaper to compute a single iteration here. And that's because the parallel Douglas-Rochefort involves a mean, and that's again a subproblem to solve on manifolds.
The cost is the cost functional, or the cost is
that's just the L2TV cost. Yeah. So that's the f of p from the last slide. Yeah, so much for that. So I'm not saying we are definitely the fastest in number of iterations. That might just be a little bit of wiggling with the parameters, might get this one also down to 113. But every iteration is much cheaper for the jumbo POC. Okay, for the second example, let's just consider Rosenbrock. So the classical Rosenbrock problem, because we know the minimizer here to be from this b and b squared in R2. And we also know that the minimizer here has a cost of 0. That's nice. But we want to make the problem mean, and to see the effect, I even choose 2 times 10 to the 5. And what we want to compare is first order methods. So just something that involves the gradient and not more. And the gradient is easy to compute with this one. And if you want to see the whole example, that's published in another package that just collects example problems on manifolds in a reproducible way. So that's what we want to compare. Now you might ask yourself, how do we get manifolds involved in here? We come up with another metric like this. So if we define GP, depending on the point P where we're at, like this, then we could say our inner product, X and Y at P is X transpose GPY on R2. Nice thing here is the inverse matrix of this is this. So that's easy to implement. And we can even write down the exponential map and the logarithmic map. And here we basically say we take R2 with the Rosenbrock metric. That's the Manifolds.jl writing of changing the metric for R2. That's the thing we want to do. The good thing is that we can even convert the gradient easily. So we had the Euclidean gradient on the last, second to last slide. Just multiplying that with the inverse of the metric tensor here gives us the Riemannian gradient. And then, so that's also tangent space vector, but on R2 that's not so interesting. But it can be actually computed from this one, and this conversion is even automatically done in Manopt. So if you have a Euclidean gradient, the Riemannian one can be computed quite schematically, and that's automatically done in Manopt.jl as well. Okay, then we want to compare, well, the Euclidean gradient descent on R2. Then we could do Riemannian gradient descent on the manifold, and we could do difference of convex, where we still have to talk about what's the difference of convex here. And it's quite easy. I take Rosenbrock, but with a +2 here instead of +1, and subtract it once. So this is a convex function, this is a convex function. The difference is still a convex function, independent on whether we are on R2 or on our manifold with a different metric. That doesn't change convexity. We start at this point 1, 2 times the 10th, which has roughly this cost, just to have the comparison. And as a stopping criterion, just to see the effect again, I take either a very small step or a very small gradient to really be sure we are at the minimizer. That's the idea. Then this is how a Euclidean gradient behaves. So it takes something like 53 million iterations. Takes a little bit of time, at least a number of iterations. Then the Euclidean difference of convex algorithm just needs 50,000 iterations. So that's, again, log scale number of iterations with the cost as a plot. That's much better. Then we could check for the Riemannian gradient descent. Well, that's still something like 2.5 million iterations. Or we could check the Riemannian difference of convex, 2,500 iterations. Now you might say, well, the Euclidean gradient or the Riemannian gradient, they just evaluate the gradient into a step. Euclidean gradient descent even just a plus, or maybe a little bit of a Mio line search or something, the vanilla one. And the difference of convex always has to solve a subproblem. So maybe they are much less in number of iterations, but every iteration might be much more costly. So if we look at the times, that's not so much the case. So yes, it is more costly, but still the Riemannian difference of convex algorithm here just takes 7 seconds to solve that, while the other ones are much, much slower than that. So that's where we win. So just as one illustration how the algorithm behaves, it's reducing the number of iterations quite a bit while still having a reasonable time because the subproblem can be solved still quite efficiently here. Okay, so what did we see today? We first saw the M-Fentier dual and the Chombo-Pock algorithm to tackle non-smooth Riemannian optimization. Then we saw the non-convex case with difference of convex, both in theory and now in 2 numerical examples. And the numerics were done in Julia, that is Manopt.jl together with Manifolds.jl, and basically both are based on Manifolds-based.jl, the interface to define Riemannian manifolds. And with that, here's a selected list of references. The slides will be available online as a PDF. That's the last link. And if you're interested in numerical differential geometry in general, maybe optimization, maybe not optimization, we also started NumDiv.geo as a Zulip chat. Just if you're interested, maybe think about joining. Thanks for the attention.
So, are there any questions in the room, or if there are questions amongst the online attendees, please write them in the chat and then I can ask them for you. Henry Bolkovich gave thumbs up. Okay, I guess I could start. I'm just curious. So you had mentioned that this is something earlier that we talked about before your talk about like including additional constraints How much harder would it be to include that with like the Manopt and all the stuff you've already implemented if you wanted to say, now I have a manifold intersected with like some additional constraints?
Yeah.
Do you see that,
that
functionality appearing soon?
Actually available. Let me get back to the Manopt algorithms overview. For the constraint case, if you have functions g of p that map into Rn for equality constraints, or h of p less or equal than 0 for the inequality constraints. So we still need that the range that you map into is Euclidean to have the less or equal or the equality. Yeah. But then you can do the augmented Lagrangian or the exact penalty method. And there's even Frank-Wolfe, but they again have the problem of a subsolver for the Frank-Wolfe subproblem, which in the Euclidean case is a linear function, and our manifolds again is a little bit more complicated. But these three algorithms already tackle constraint problems. So if you're on a manifold and you have additionally equality or inequality constraints, that can already be tackled. And then you, of course, have to implement F, G, and H. Yeah, understood.
So like if you have a sphere, you can have like a piece of the sphere that you sort of...
Yes, if you can describe that with G or H, you could, for example, restrict yourself to 1/2 if you say the first component has to be positive. Or even 1/8 of the sphere by saying the first two components have to be positive.
There was a question by Stephen Moore. He said, is this a finite difference discretization of the manifold?
No, the manifold always stays the complete concept of the sphere, so the continuous sphere, and we always work on the complete non-discretized manifold. So same for Stiefel or for the Grassmann manifold. That's the complete set of all basis matrices that are orthonormal basis. No discretization on the domain side of F.
I assume that answered his question. Yeah, so he said thank you.
Ah, yes.
Great. Any other questions? Seeing none. Thank you again, Ronny Bergmann. And see you all next week.